Welcome to Lesson 8.8. We are modeling exponential growth and decay. This is a continuation of 8.7, which we talked about exponential functions. So exponential growth, as we talked about yesterday in 8.7, is y equals a times b to the x. Now, the difference between yesterday and today is that we now are going to look at this base here. When this base is greater than 1, okay, so the number is 1, 1.5, 2, whatever, that means things are growing, okay? And when we have that base, b here, and it's between 0 and 1, that means we're losing something. So think about the when we started the photocopy example with 90%. We were only taking 90%. And I talked about having $100 and then 90, and then we lost another 10%, which would be $9, and we're down to 81. So these equations are set up the same way. We have the x in the variable, or the exponent is a variable, okay? A is our starting value, and then B is our growth factor, and when we're decaying or losing, B is our less than 1, and that would be our decay factor. Compound interest. Compound interest is the interest earned on the principal as well as the interest. So if you're earning interest on the interest, and then interest period is the length of time the interest is calculated. Now, one important note, if you are given an interest rate, okay, unless otherwise stated, you have to assume that it is an annual rate. So if they say you have an interest rate of 10%, you're not getting 10%, even though your interest might be compounded monthly or daily. You are not getting 10% every month. You're only getting 10% over the course of the year, and they give you a little bit or a percentage of that each month. So let's look at some compound interest problems here. So let's suppose that you have $1,000 in a fund, and it pays 7% increase compounded annually. So that means each year you're going to get 7.2%, okay? So if you go to your function rule, y equals a times b to the x, x is going to be 5 because that's the number of times that the interest has been compounded. If it's compounded annually, which means yearly, and after 5 years, you would have compounded your interest 5 times, okay? $1,000 is what you're starting with. So A is going to be our 1,000. Now, the B value is the tricky part. Our B here is 1.072. Remember, we're adding or increasing our balance by 7.2%. So in order to get this B value, what you need to do is you always start at 1. Okay, you're starting at 1, and then if you're increasing or growing the amount, you're going to add that percent to it. So remember, 7.2% as a decimal is 0.072. Add that to 1, you get 1.072. This is going to be your growth factor here, this 1.072. That's your growth factor, and then that is going to be taken to the 5th power because that is how many times our money has been compounded, okay? So we can then plug this into our calculator, and after 5 years, if we invested $1,000, after 5 years at 7.2%, we would have $1,415.71. Not too bad. Definitely want to make sure you have your calculator handy and you know how to operate it. If you have any questions, ask in class and not before the test, please. Let's try another example here. So we're compounding interest, the same one, except now the interest is compounded quarterly. So what I want you to think about is you were given 7.2%, right? So we were given 7.2% annually, okay? So if our interest is compounded quarterly, okay, quarterly here, that means 4 times. So we're going to divide that 7.2 by 4 and we get 1.8. Okay, 1.8% is the amount we're going to get every quarter. Okay, so we get 1.8% after one quarter, and then we get an extra 1.8% after the second quarter, and then another, and so on. Now, after 5 years, how many quarters have we had in this case? And 5 times 4 is 20. So you can see here, we take the 1.8%, we add that to 1, and that is our growth factor. So we're not getting as much each time, but we're compounding our interest 20 times as opposed to 5. And you can see here by our balance that it actually gives us more money. So it's better for us to have our interest compounded many more times. Even though we're getting a little bit each time, it's better to get a little bit each time and earn interest on the interest than once every year. Banks and credit cards love to play the numbers game, and they may give you an annual interest rate, but they love to compound their interest daily. So think about the fact that you're paying interest on the interest when banks are charging you. Think about credit card rates. They're compounding the interest 365 times. Yeah, it's a lot. I'll try to do one of those problems in class just to show you what happens to a $20 credit card balance here if the interest is compounded daily. All right, go ahead and try a couple quick checks. Remember to think back to y equals A, starting value, times B, which is your growth factor, to the x power, and the x is always your generation. In quick check 1 here, go ahead and pause it. Whenever you're ready, start it back up. So we've now changed the interest rate to 8%, okay? And we're going to only compound it annually. So we upped it just a little bit, and we're going to let it sit for 18 years. So here's our equation, and after 18 years, you've taken that $1,000 that we had in example 1, and you now have almost $4,000. So you have quadrupled your money in 18 years by earning 8%. Not too bad of an investment. Let's suppose we deposit $200 into an account earning 5% compounded monthly. How much will the account have after a year, 2 years, and 5 years? Okay, so here's the equation I came up with. Right here, y equals 200. That's our starting value, right? And then our growth factor is going to be 1 plus, and I'm taking that 5%, but I'm only giving you a part of it each month, so I divide that by 12. Okay, and so to not lose any decimals, because I know you guys love to round, I just put that in parentheses and kind of leave it there in my equation. You can actually enter this entire equation right into your calculator and then look at the table. Now you have to think about the fact that 1 does not represent 1 year, but 1 month. And so if you were looking at how much you would have after a year, your $200 investment after a year, 12 months, would be $210.23. So you've earned $10.23 interest by compounding it. Think about if you only earned 5% every year, you would only have $210. So that extra 23 cents is what you're getting by having your interest compounded monthly rather than annually. And then after 2 years, which is 24 months, again, you can use your table to check this out as well, or you could plug in 24 for X and compute it that way. You have now $220.99. So earning interest on that interest, we've gotten a little bit more. And then after 5 years, which is 60 months, we now have $256.67. So we can see how compounding interest really is beneficial to us, but can also be to a detriment if this was your debt. Moving on to a decay. So here is a model for our decay here. We have an endangered species that is decreasing. We're losing 2.5% of the population each year. And so if we start out with 60 of these animals in a given area, how many are we going to have after 1 year, after 2 years? When are we pretty much going to be down to a half an animal, which we can't have, and we know that they're extinct now? So to write this, we follow the same rules. A is our starting value. A is 60. Now, with our growth factor here, we're actually decreasing. So we're going to take that 1 and we're going to subtract the 0.024 from that, okay? 1 minus 0.024, and that's going to give me the 0.976. So every year we only have 97.6% of what we had the previous year. Hopefully that makes sense to you. We're losing. If we had the 1 in there, we would be maintaining along the way, but we don't. We're losing 2%, 2.5% or 2.4% each year. And X is the number of years in this case, okay? So then if we want to know how many animals are going to happen after 2005, remember 99 is when we had here, so we actually have 6 years that have passed. Okay, so at the end of 2005, if we plug in 6 as our exponent here and plug this into our calculator, we now only have 51.86 animals. Now, obviously, we can't have 0.86 animals, so we may have 52 or we may have 51, depending on the year, but we are losing 2.4 animals, or 2.4% each year. So our population, we've lost quite a few of these endangered species each year. Go ahead and try the next quick check. Restart when you're ready. So we have the population in 1990 of Washington, D.C. is 604,000 people. The population has been decreasing at the rate of 1.8% each year. So here's my model. Here's my model. And then here's my model. Y equals my starting value. This is my decay, my decay factor here. Remember, I'm losing 1.8%. 1 minus 0.018, which is the decimal point 0.018. Remember, that's a 1.8% decay. Subtract that from 1, we get 0.982 to the x. And then if we wanted to know the population in 2010, which is 20 years have passed, okay, we can plug that in, and we get that we are down to about 420,000 people. So we can see the population decreasing there. Again, we're going to be doing more examples in class. I hope this is starting to make a little more sense to you. Again, if you've got questions, please email me or write them down and ask in class.